This lesson on thermal physics takes a look at changes of phase, and here are your objectives. In this graph, we are graphing temperature on the y-axis against energy that we are adding. And so energy is on the x-axis. Or if we were adding that energy by applying a heater, for example, with a constant power output, this could be time. As we continually add energy, starting from a solid phase, we see an increase in temperature. So we've started from a solid, we see that solid increasing in temperature. At a certain point, though, when we continue to increase the energy or add energy, we don't see any more increase in temperature. What's happening here is that the solid is melting, and so we have a mixture of both solid and liquid together. So let's say that we're dealing with water. We started with ice. This would be at 0 degrees Celsius here. And even though we're continuing to add energy, we don't see the ice-water mixture increasing in temperature until all of the ice is gone, and then we just have liquid water. Once we just have liquid water, the temperature would increase again, and that would continue until we reach the boiling point of the water, here 100 degrees Celsius, at which point now we would be boiling, and we would have a mix of liquid and gas. Once everything became gas, there was no more liquid, then the steam, in this case, would start to increase in temperature. So we see that there are these phase transitions, these changes from solid to liquid and liquid to gas, that occur at constant temperature. And the temperature doesn't keep increasing, even though we keep adding energy, we keep moving to the right here. The temperature doesn't keep increasing until we are entirely in one phase again. So once we get all of the solid melted, we start to increase the temperature of the liquid. And then we see the same thing here again at the boiling point as we move from liquid to gas. Adding more energy, moving to the right on the graph, doesn't give you any hotter water. All that happens is you turn it into gas more quickly, and then once it's a gas, it will increase in temperature. And that's why when you're boiling something on a stove, turning the element up higher doesn't make it cook any faster, because you can't get the water above 100 degrees Celsius at normal pressure. You could in a pressure cooker, but you can't get it above 100 degrees Celsius. All adding that extra energy is doing is turning more of it into steam. Let's talk a little bit more about evaporation, boiling, and condensation. Evaporation happens at the surface of a liquid and happens over a range of temperatures. And what's happening is that the particles with the highest kinetic energy have enough energy to break free of the liquid phase. Now, if you think about it, if the particles with the highest kinetic energy are leaving, that means that the ones left behind have a lower average kinetic energy than they did before those particles left. Again, the highest energy particles are leaving, therefore the average kinetic energy of all the particles left over is going down. And remember that temperature is a measure of average kinetic energy, and so evaporation is a cooling process. That's why we sweat to cool down. The molecules of sweat that are leaving the liquid phase to the gas phase as the sweat evaporates from our skin is cooling the sweat remaining, and that's drawing energy from our skin and cooling us as well. Boiling is the same kind of thing, but it happens only at the boiling point and happens throughout the liquid. So imagine a bubble forming at the bottom of a boiling pot of water here. Again, higher energy particles are going into the gas phase and forming this bubble. The difference is that they are doing it throughout the liquid. But again, as those particles leave the liquid phase for the gas phase and then leave the pot of water entirely, they're leaving behind lower energy particles, and so boiling is actually also a cooling process. We might mistakenly think of boiling as a heating process, but it's actually the element below that is heating the pot of water. That's the heating process. That's adding energy to the pot. Boiling is actually taking energy out of the pot. So both evaporation and boiling cool the liquid that is left behind. Here the water's not cooling because we continue to add energy to it from the element. Again, because of this process of removing the highest energy particles. And the reverse is also true. Condensation, going from the gas phase to the liquid phase, releases heat, and so does freezing as well. So an example of that is steam burns. Steam burns are very dangerous. In fact, steam at 100 degrees Celsius is much more dangerous than water at 100 degrees Celsius, because when the steam hits your skin, it condenses, and that condensation releases a whole lot of energy from the steam to your skin. Now let's talk about what's happening at a molecular level when the phase is changing. During those horizontal parts of the temperature versus energy graph, the melting and the vaporization, the energy that's being added is going to increase the potential energy of the molecules. In other words, it's going to overcome intermolecular forces, or IMFs, or bonds, between molecules, to therefore allow molecules to move away from each other. Because the energy being added is going to potential energy, it's not going to kinetic energy, and so the average kinetic energy does not increase. And remember that temperature is a measure of the average translational kinetic energy of the molecules. Once all of the substance is in the same phase, the average kinetic energy can start to increase again as we continue to add more energy, and therefore the temperature increases again. But during those phase changes, the energy being added is going to increase potential, not kinetic energy. And just like specific heat capacity allowed us to quantify the energy that was needed to raise the temperature of something, we can quantify the amount of energy that's needed to change phase. And we do that with the latent heat of fusion and vaporization. Fusion is a synonym for melting. And the latent heat of fusion and the latent heat of vaporization refer to the energy as heat required in order to get a unit mass of a substance to undergo a phase change, or released if we do the opposite direction phase change. And we quantify them with a formula very much like what we saw for specific heat capacity. Here the heat energy is equal to the mass multiplied by L, the latent heat of fusion or vaporization. And the units of L are joules per kilogram. We don't need a degree Celsius here because the temperature is not changing. Let's look at a typical example. We have ice at 0 degrees Celsius added to a cup of water at 20 degrees Celsius. So here's my water, it's at 20 degrees Celsius, and I'm going to put some ice in it. And the ice is at 0 degrees Celsius, and we're given the masses of each. We're told that when the mixture reaches equilibrium, some ice remains, and in fact we're going to interpret that as some ice and some water remains, both. We're given the latent heat of fusion of water and told that no heat is exchanged with the surroundings. Find the mass of the ice that is melted. So again, the only energy exchange here is going from the water into the ice. And so now we can set this up as Q out from the water is equal to Q in to the ice. And if there is ice and water remaining at the end, then we know that that must mean that the temperature at the end is 0 degrees Celsius. That's the only temperature that we would have both ice and water. So that's our clue. And we set this up as mass of the water times the specific heat capacity of the water times the change in temperature of the water, because the water is not going to change phase. It's remaining as water at the end, is equal to the mass of the ice times the latent heat of fusion of the ice. The ice is changing phase, but is not changing temperature. It's still at 0 degrees Celsius. So the question is a little bit simplified by the fact that one thing is changing phase but not temperature, and one thing is changing temperature but not phase. Now we just plug things in. So we have 0.300 kilograms of water multiplied by the specific heat capacity of water multiplied by the 20 degrees Celsius temperature change, and that's going to be equal to the mass of ice, which is what we're looking for, multiplied by the latent heat of fusion of ice. And when we solve for m, we get 0.3 times 4,186 times 20 divided by 3.3 times 10 to the 5, or approximately 0.0750 kilograms, or 75 grams. So that's an introduction to a calorimetry problem involving a change of phase and latent heat of fusion.